Hello friends, good evening and welcome to my YouTube channel with my name Yukul Pachori. As we all know that I do post videos related to different topics and continuing our series on electronic devices and circuit. This is my third video for the discussion, and we are discussing the electronic devices and circuits, that is the basic electronics or the fundamental electronics, or you can say the applied electronics as well. I mean the concepts of electronic devices and circuits are useful in this subject that I just mentioned, that is the basic electronics, fundamental electronics, and the applied electronics. So let's continue our discussion, and let me share my screen with you all. I hope my screen is visible to everyone. Now let me open the book or the source of our discussion, that is a Boyle state. We are discussing all the content from the book that is known as the Robert L. Boyle state. So let's continue our discussion and understand what is breakdown. Breakdown means, as you can see this from this particular image, this is a graph between the voltage and the current. As you can see in the forward bias region, when the P is positive and N is negative, this is the forward bias. This region is the forward bias region. Let me change the pointer. Okay, this is fine. You can see this. This is forward voltage and this is the forward current. As the voltage is increasing, the current is also increasing at certain point, and beyond a certain point it will be saturated, and after the saturation there is a point that is known as a breakdown. So in layman language, or in just a simple term, we can understood the breakdown. Suppose we are riding a vehicle. If we go to a certain speed, it will ride. If we go beyond certain speed, the speed will not increase. However, there will be wear and tear in between that vehicle, and the vehicle tends to break down. So the same thing happens with the diode. Like if we increase the current beyond a certain point, the diode will not be able to withstand the current, and it will go into the condition that is known as the breakdown. And the voltage at which the breakdown happens is known as the breakdown potential. So you can see in this graph, this is the forward voltage, this is the reverse voltage. As soon as the reverse voltage is applying at a certain point, at this point, there will be breakdown. Means infinite current is flowing from the device, or the device got breakdown, or the device got ruptured. Means it is not working properly. That's why it is called the breakdown condition. So you can easily understood from this graph, this is voltage, this is current, and this is the forward characteristics, and this is the reverse characteristics. Now moving on to our next topic. There are two types of breakdown. One is avalanche breakdown, and other is a Zener breakdown. The Zener breakdown is due to the heavy doping, and it occurs at a certain different voltage, whereas the avalanche breakdown is due to the impact ionization, and it occurs at a different voltage. One occurs at the low voltage and other occurs at the high voltage. This is the condition of the breakdown. So there are two types of breakdown. One is the Zener breakdown and other is the avalanche breakdown. And I told you the avalanche breakdown occurs due to the impact ionization, and the Zener breakdown is appears due to the uh, heavy doping characteristics. So let's and continue our discussion. And as you can see, germanium, silicon, gallium arsenide. The discussion though thus far solely use silicon as a semiconductor material. It is now important to other two materials, gallium arsenide and the germanium. I already told you in the beginning of my this series, either in the first video or the second video, that silicon is preferred. Why I told you? Because silicon is abundant in nature, and it is abundant in nature, and plus also it has a high thermal stability. That's why the silicon is preferred. Now, same thing happens with the gallium arsenide and the germanium, but the preference is more for silicon. But however, it does not mean that we are not using gallium, germanium, or the gallium arsenide. We are using these two other than silicon also. Okay, so you can understood this concept from these two, this graph. This is the current condition for the germanium. First graph is for the germanium, second is for the silicon, third is for the gallium arsenide. So if you compare which has the lowest cut-in voltage, The lowest cut-in voltage is for the germanium, that is 0.3. The second highest cut-in voltage is for the silicon, that is 0.7, and the highest cut-in voltage is for the gallium arsenide. So out of this, if we compare in terms of the cut-in voltage, which will be preferred? The germanium will be preferred. But the silicon is abundant in nature and it has comparatively higher than germanium, but lower than the gallium arsenide. That's why the silicon is more preferred. So these are the characteristics on the this first quadrant is of the forward bias condition. And this is the second quadrant. There is no current flowing over here. And this is the third quadrant. And this third quadrant characteristics is for the reverse bias condition. And you can see the breakdown is happening in gallium arsenide as the highest voltage. The breakdown is second in the silicon. That there is a very low, the breakdown is happening at the very low voltage in case of the germanium, but at a higher current. So with this characteristics or the analysis of this graph, you can understood the breakdown characteristics of different germanium, silicon, and gallium arsenic. This is the point. Now, let's continue our discussion. You can see the knee voltage. I was talking about the cut-in voltage or the knee voltage. Knee voltage is germanium 0.3. You have seen in this graph. And silicon 0.7, gallium arsenide 1.2. Knee voltage is also known as the cut-in voltage. So this is our discussion. Let's continue it. And what about the mobility? What is mobility? The mobility of electron is higher than the mobility of holes, but the mobility is a tendency of any charge, of any free charge carriers to move freely. That is uh, mu is equals to Vd over E. Means centimeter per second over volt per centimeter. So hence the unit comes out to be centimeter per volt second. And you can see in this particular centimeter square. Just a second, let me pause. Let me pause the recording. I have a call. So sorry for the interruption. I got a call from one of my friend, and let's continue our discussion. I was discussing about the mobility, and the unit of the mobility is centimeter square per volt second. And basically, the definition of mobility is that it is the ability of the charge carriers to move freely, and it is given by a formula mu is equals to Vd over E. Vd is a drift velocity, and E is the electric field, as you all know about this. Means mu is equals to drift velocity over electric field. And what is mu? Mu is mobility of the charge carriers to move freely, mobility or the ability. Okay. So if you want to do some questions, you can work out this question in the PDF of this particular book. Now let's understand what is the effect of the temperature on the semiconductor material that we are going to use. So what it says that temperature can have a marked effect on the characteristic of a semiconductor diode, as demonstrated by characteristic of a silicon diode. So there is an effect of temperature on the characteristics of the silicon diode, germanium diode, or the gallium arsenide diode. It means whichever material you're going to use, it will have the effect of the temperature on that particular kind of the semiconductor diode, whether it is made from silicon, germanium, or the gallium arsenide. So let's understood with the help of these characteristics. You can see when the temperature is 125 degrees Celsius, the current is flowing a bit faster. I mean, higher the temperature, the current will flow faster. There is no knee voltage or there is no cut-in voltage. Now, as soon as the temperature is reduced to 25 degrees Celsius, there will be certain cut-in voltage. As you can see over here, I am pointing out over here. There is a cut-in voltage and the current is increasing slower. And when the temperature is reduced further, then there is more cut-in voltage and the current is increasing slowly. So as soon as the temperature is decreased, the rate of the current rate of the increasing of the current gets reduces. That's why it is called effect of the temperature on the properties of the semiconductor. So it means in the conclusion, we can say that the properties of the semiconductor diode is changing with the help of the with the effect of the temperature. When the temperature is higher, the current is increasing faster, you can see the first characteristics. And the second, when the current is, when the temperature is little bit higher, then it is increasing faster. And when it is lower, the current is increasing very slowly. So as soon as the temperature is increasing, the rate of the increasing of the current get decreased. And same things happened in the third quadrant, that is the reverse bias condition. So you can compare both these analyses, the forward bias and the reverse bias, and it is clearly depicted in this picture, the 125 degrees Celsius, 25 degrees Celsius, and 75 degrees Celsius. So there is, yes, there is an effect of temperature on the properties of the semiconductor diode. Now let's move to the another topic of our discussion. Another topic, that is the reverse bias condition. In the reverse bias region, the reverse saturation of a silicon diode doubles for every 10 degrees Celsius rise in temperature. So suppose if there is a reverse current, then there is a condition if the temperature increases by 10 degrees Celsius, then the reverse saturation current will be doubled. It becomes twice. So if the T is equals to 10 degrees Celsius, there will be current I1. If the T is equals to 20 degrees Celsius, the current will be 2 into I1. Why? Because there is an effect of temperature with the every 10 degree Celsius. Now, another point, the reverse breakdown voltage of a semiconductor diode will increase or decrease with the temperature. So the effect of the temperature is also on the, what you say, is also on the, effect of temperature is also on the breakdown. If the temperature is increased, the breakdown will happen earlier. If the temperature is decreased, the breakdown will happen at a higher, at after higher voltages. So there is an effect of temperature on the breakdown condition as well. And as you can see this picture is a very nice picture. A certain two gentlemen are working in this laboratory kind of thing. Let's read about this. Russell Ohl, he's lived from 1898 to 1987. He's an American, Allentown, PA, Homan, held NJ Vista CA Army Signal Corps. So they are working in Army Signal Corps, University of Colorado, Westinghouse AT&T Bell Fellow Institute of Radio Engineers, 1955. This picture is from 1955, and this has been taken with the help of the AT&T Archives History Center. So you can understood the kind of the work that are being available in the electronics and the kind of, and like suppose if I'm preparing this lecture or the concept overview or the discussion with the or the talk with the help of the YouTube, and you're able to watch this. So this is the advancement in the technology that has happened, that I'm able to deliver a lecture with the help of the YouTube channel, and you are getting the benefits from the YouTube channel. So I think that's it for today's discussion. Now, before winding up, I will tell you what is the ideal diode and the practical diode. Basically, there are two types of concept. One is the ideal concept, and other is the practical concept. However, there is nothing like ideal. Ideality exists, but in practical terms, it doesn't exist. We are trying to achieve the best factors, and the best factors are known as the ideal factors. However, the things which are pragmatic or practical are um, slightly bit different from the ideal things. That's why it is called practical things. So ideally, if the diode is forward bias, it acts as a short circuit. If the ideal is reverse bias, it acts as a open circuit. I already told you in the previous discussion in the video number 1 or video number 2. So if the diode is reverse bias, ideally it works as a short circuit. The diode is reverse bias, ideally it works as an open circuit. So you can understood. Now, and these are the practical characteristics. Ideal characteristics are straight away high and straight away low. And same as we have the different resistance level. So, but practically, the diode behaves something different. It has some cut-in voltage. After the cut-in voltage, the current increases. So the cut-in voltage is 0.7 for silicon and it is 0.3 for the germanium. And in the reverse bias condition, it also behaves something like this. You can understand with this graph. If the current is increasing slowly and beyond a certain point, there is a breakdown. I already told you the concept of the breakdown. So I'm stopping over here. And the next video, we will continue our discussion with the resistance level what kind of what are the characteristics in terms of the AC resistance or the DC resistance. We will discuss this in our next video. And let's summarize the today's video. We have discussed uh, the ideal diode. We have discussed the uh, breakdown condition. We have discussed the effect of temperature, and we have discussed the two types of this what you say breakdown mechanism, that is avalanche breakdown and the general breakdown. And we also discussed that we can use germanium, silicon, gallium arsenide in for the application of the semiconductor diode. It means we can use any of these three material, and there are some other materials as well for the application of the semiconductor diode. It means we can make a semiconductor diode from any sort of material that are available for the semiconductor purpose. It is not that we have to stick to silicon only, or we have to stick to germanium only. We can use any of these. So that's it for our today's video. I hope you got things clearly, and things are. If you have any questions or any comments or suggestions, you can post them. I'll be happy to answer all your questions, and I'll be really happy if you have any suggestions also. So thanks for watching. Have a nice time.